Hi everyone, welcome. This is the relational model from week 2. We're going to be talking a bit more in depth about how these relationships work, a bit about good design, and then just kind of what you can expect before we delve into some more relational algebra for week 3. Great. So if you watched the previous videos and the previous slides, essentially we saw a relation as a table where we have attributes and each row is going to be a tuple. And again, a tuple is with the first familiar with Python, the commas inside of the parentheses or the rows that we have here. So again, a table or relation is going to be the full table. So this is our relation that we're looking at. Each relation is going to have an in-depth of attributes and then data for it. So what we want to look at is actually the types that we're looking at inside of our SQL and database design. Again, if you're coming from object-oriented language, you might have heard stuff about primitive types or built-in types such as integer, floats, strings, and booleans. Those are applicable here, but we're going to be looking at different types, if that makes sense, for our SQL. So the set of allowed values for each attribute is called a domain, or the data type of that attribute. This is similar to what we said earlier with our static languages. If I say that a variable x is an integer and I assign the string John to x, I'm going to get an error if it's a static language because I am trying to apply the wrong data type to that attribute or variable. So attribute values are normally required to be atomic. And when we say atomic, that means that they're indivisible. This means that they might be integer values or addresses or something that is set inside of there, okay? So essentially, you might be thinking my ID value of 5555 is technically divisible by a number, but actually we just want it to be atomic or set inside of there. We can see here the not addresses here of street, city, zip code, state, and country might not be applicable as well in some senses. So essentially, you could have the numbers inside of your atomic one, but essentially, we're going to have stuff that is indivisible for that one there. Okay. So a special value null is something that we might have seen earlier. You might have seen it as nil or none in other languages too. This means that it's unknown or not applicable. So regardless of the data type or the domain that you call it for your attribute, all of them can be null. The null value causes complications in the definition of many operations, which we talk about later. But essentially, you might have a relation where you have all these variables filled in, but for some instances, it might be null, which might cause issues. Cool. So we're going to look at a bit of math, but I'm just going to break it down pretty simply, and it shouldn't be too complicated for us. So when we look at relation schema and instances of our schema, so essentially what it is looking at that time, the A's inside of our language that we have here are attribute names. So this might be A1, A2, and AN. So A1 is going to be my first column of the information down. A2 is my second one, and then AN is my nth column going down. Okay. So R, my relation schema, is the attributes of all of them. Okay. So if we go back to this again, A1, A2, A3, A4, AN over here if we don't have it. All of this table is R for our relation, okay? Instructor is equal to ID, name, department name, salary. It's what we saw earlier. So this is what we have from that table. So if we try to formalize this, if we're given sets D1, D2, and Dn of domains, a relation R or relation instance is a subset of D1 by D2 up until Dn, okay? So we have these domains, which again is just our columns here. And these are relation instances, and they're going to be subsets, right? So I can kind of take D1, D2, D3 here, these three guys, and that's going to be a subset of R, my overall one. So essentially, this is kind of a formulaic proof that's saying a relation is a set of n tuples, where each A of I is the summation of all of them together, okay? So my A1 up until AN is going to be all of, excuse me, all of the full domain there, okay? So again, this is kind of straightforward when we look at it in terms of the actual image. So each column makes up the full table, but this is kind of what it looks like when it's breaking down into all of these. Again, the word tuples comes up here where each of these rows are shown to us, but we'll take a look at that in a bit as well. Cool. And we can look at it here where the current values of our relation instance of a relation are often specified in a tabular form. So we might think of this idea as if they're ordered or unordered. Now, there's one caveat here that we have is that if we have a set, the tuples of the relation do not have any order defined as implied by the tabular representation. Okay. This means here is that when we get back the tuple of these, they might not be in any particular order. So essentially, Einstein and Mozart might not always be in this order on top of each other. And then if we call select all from table R, we might not get ID before name sometimes. Okay. An element T of R is a tuple represented as a row in a table. So each T or tuple that we get back is going to be a row. And there's some more alternate definitions here. Sometimes tuples are defined as functions from attribute names to values. So t.name is equal to Bob, or tuple name is equal to Peter. And these are useful when we're looking at the theory behind all of these as well. But this class is a bit more practical on it too. The book delves into the theory a bit more heavy too in chapter 1, chapter 2. But essentially what we're trying to look at here is just that all of these are kind of subsets of what we're doing. And it's important to know the kind of overall definition of it, because that will actually help you when you're coding the SQL code. Okay. What I said earlier is that relations that we have are unordered. So a relation is a set. The elements of a set are not ordered. So from a practical perspective, the order of tuples is irrelevant. Tuples may be stored or returned in any arbitrary order. So CS4071, sometimes it might be 7071 CS, stuff like that too. So if we have instructor relation with unordered tuples, we have ID, name, department name, salary. If we go back here, we could see that Einstein was actually at the top previously, but he was down here at the bottom. So we might be thinking, is this an issue, right? Because usually you want to have some form of order. If you remember your data structures course, we were trying to sort things into a certain order with some of these algorithms. It's not necessarily an issue because when we try to do our non-procedural language, we're still going to be able to get the data that's there, right? So just because they're not in order doesn't mean that our physics department's faculty aren't there, okay? Cool. So this is some more vocabulary about a database itself. So database schema S consists of multiple relation schema. A database instance I for a schema S is a set of relation instances. So there's for each relation, there's one relation for each relation schema in S. And then when we're taking a look at this relation, we can be broken into a few parts here. So again, our overall schema is going to be consisting of multiple relations, but the instance of it is where we have it at that brief time. So let's just say that we're dealing with this type of client that wants to talk a bit about the instructor, student, and advisors in their university. We could attempt a design that says in the university, create a tuple that has my instructor ID, the name, the department name, the salary, and the student ID. Why is this really a bad design? Well, first of all, we have repetition of information. We have two students that might have the same instructor, right? So if we have the same instructor, we're going to have the ID be the same. Most likely the name of the instructor be the same too. Now, what happens if we have the need for many null values? What happens if we have a student with no advisor? Okay, so later on, we look at normalization theory, but again, just kind of get it into your head of thinking about, okay, do I need all this information for this tuple, or is there a way I can make it more precise with what I'm working with? Okay. This is what we saw earlier as well. But again, if we forget to update a row and we have multiple budget values for the physics department, this is where things can get very messy. So essentially, because you're assuming that there's concurrent design, this is from the previous video too. But if physics has 70K down here and then 80K over here, because we decided to update the row without doing a row update everywhere, that will be an issue. We'll look at how to actually do that in SQL, but essentially that might be something useful later. Cool. Just some more bad design examples here too. How do we avoid deleting the entire physics department inside of our department name? Is there a way to reference it later on? Stuff like that. And again, sometimes you might be thinking use dummy employees so that maybe we might have just 0 Lynch, 0 physics, and then the building here as well, like null building. That might be useful when you're just starting out. But because of that, we're going to have, for instance, if we say, if I'm storing physics as a dummy variable, just so I don't delete it, and then I forget about it later on in the day and I try to get how many departments are in my university, and instead of just having like 6, that is the culmination of the ones that are here. I have 7 because I have a dummy physics department that can cause errors, right? So that's just a bad design. So when we're taking a look at our keys, we have multiple types of keys that we might have, a super key, a candidate key, and a primary key. So essentially, going from the bottom up, a primary key is what's going to identify a relation for us. It's what we saw earlier where we have ID as the instructor primary key to identify it. A candidate key here is a bit more unique where we have it, excuse me, where we have a candidate key where it's going to be able to uniquely identify a person if it's minimal. So essentially, if we have the least amount of columns to uniquely identify a row inside of our relation, but if any of those columns are removed, then it no longer becomes a unique identifier. Okay. So for instance, a candidate key might be ID and salary. Another candidate key might be ID and name. So it's 2 columns put together or attributes. But essentially, if I remove name from Einstein, I won't be able to use it as a unique identifier anymore. Something along those lines, but essentially use 2. And super key is one that uses more than one attributes, similar to candidate key, but some of these might be extra. So essentially, super key might be ID, name, and budget. Budget's not very necessary for super keys, but we might use it anyway. Okay. To actually take a look at the keys here, K is a super key of R if values for K are sufficient to identify a unique tuple of each possible relation R of everything. So ID and ID name are both super keys of instructors. So again, it's sufficient to identify a unique tuple. That doesn't mean that it has to be the least or the max amount. That just means that it can do it. So as I said earlier, it could be ID, ID name, budget, salary. So all of these are super keys. There's a super key just has multiple attributes. A candidate key is a bit more unique, where super key K is a candidate key if it's minimal. So no subset of K is also a super key. What this essentially says that if I take away any of the extraneous attributes that is a part of my super key, I can no longer identify a unique element there. So essentially, ID is a candidate key for instructor. Okay. So if I have 2 super keys here, I can use them both. What happens if I remove ID from my candidate key? Or excuse me, if I remove ID from my super key, I can't do anything anymore, right? Because I don't know how to identify anyone. It's just a blank key. So that means that it's now a candidate or a super key. Sorry. So it's a little tricky sometimes to mix them up, but essentially super key could be as many as you want. Candidate key has to be the minimum amount, or it's minimal in that sense. And then a primary key is what is going to be selected after you get your candidate key. Okay. So again, super key comes first when you're designing it. Get it minimal to your candidate key, and then whichever candidate key you like, you pick it for your primary key. Again, this one says which one is a domain-specific design choice. The vocabulary can be a little confusing. It's straightforward enough, though. It's usually going to be an ID, but it might be something different based on your design choice. Okay. So we also have these foreign keys here, and I won't read off the full arithmetic definition here because it's a little wordy and it might sound a little weird doing it too. Essentially here, for our second bullet point, we want to make sure that a foreign key holds over an instance between 2 relations, the ones that we're looking at, if and only if all the values of our schematic of R are also in the other table that we're looking at. This isn't what it says right here, but if you look at it visually, what we're trying to do here with our foreign keys is that we want to reference a relation in a different relation, reference an attribute in a different relation, and also have that attribute in the referencing relation, okay? So a foreign key is going to be something that connects you to a different relation somewhere else. And they have to have the same attribute, essentially, because it's what's connecting them together. So a department name here is going to be referenced over there. And it doesn't mean it's vice versa, but you could potentially do something along the lines of that. Essentially, what this arithmetic definition is telling us is to go ahead and reference whatever is here into your department. And then you can kind of get the budget from over there. Cool. So now that we have all these primary keys and all these types of keys going on, we can actually start doing some of these schema diagrams here. Okay. So if we start off with a section, we have a couple keys that we're looking at here. If we trace this one back up, we can see that a course ID is taken over here. We might actually start off with the student itself. So ID is referenced by multiple places here. It's a foreign key in two other relations. The primary key of student is department name here, and that's relations to a foreign key department name. Department name, course and references department, and so forth. So I won't go through all of it, but you can see here when we have this underlined, it's our primary key that we're looking at for our table, and a student has these attributes, okay? And again, this student table these are all columns inside of this full table, and then this is how we reference it. So this looks like a lot, but this is kind of where our relation schema comes from and how we're thinking about designing it. And when you're making your models and trying to design your final project, you'll most likely be doing something like this with all the different things that are going on. One more thing here, with these guys here, department name is referencing over here this department name. That means that that's a foreign key, okay? So department name is referencing a foreign key department name in the table or the relation department. Cool. So there's a bit of a recap here. Take a look at the integrity constraints as well. But again, these types of vocabulary are talked a bit about in chapter 2. So I would double check that as well. You don't need to worry a ton about all the individual items here. What I would say is that if you go through this video and if what is going on here is making sense and you can kind of think of all these as tables and think of them as attributes inside, each of them as rows, these attributes as having columns inside of the table, then you should be good to go. Thank you.